States of matter, part 1. Previously, students learned that under ordinary conditions on Earth, there are 3 phases of matter: solids, liquids, and gases. In this illustration, the red spheres represent atoms or molecules in those different phases. Now, a solid can become a liquid, and a liquid can become a gas. And these phase changes can occur when energy is removed or added to a sample of matter. The reason why a gas will completely fill its container when a liquid will not is a difference in the amount of energy that is available. Reactions that add energy to a system are said to be endothermic, that is, the energy goes into the system, while those that release energy are exothermic, the system is losing energy. We can imagine beginning with some solid, putting some energy in. It undergoes a phase change, it melts. So we have a liquid. If we add in more energy to the liquid, it will evaporate. A gas is produced. We can reverse the process, removing energy through condensation. The gas turns back into a liquid. Removing in even more energy, it freezes back into a solid. Now, in addition to these very familiar phase changes that all of us have seen in everyday life, we have this. A solid can sometimes skip a step. It is said to undergo sublimation. Instead of turning into a liquid when we add energy, directly converts into a gas. In the reverse process, the aerosolized gas directly converts into a solid and deposits back into the environment. In all of these examples, the arrows that are going to the right are endothermic, energy is being added, and those that go to the left are exothermic, energy is being removed. Now you might ask why it is that some substances, say like carbon dioxide, will skip a step and go directly from a solid to a gas. Well, it has to do with the pressure that is on those items. So endothermic and exothermic processes, as described, are promoted by local changes in pressure or local changes in temperature or both. Local changes in pressure and temperature are important in determining things like what phase matter is in. It is often necessary to take measurements of temperature and pressure in order to study phases of matter. And since there are multiple units for both temperature and pressure, it is often necessary to convert from one unit to another. To measure pressure, the traditional way to do it is with a device called a barometer. Pressure can involve different units. For example, 1 kilopascal, kPa, equals 1,000 pascals. These are both metric units. But the pressure of the atmosphere at sea level is sometimes simply called 1 atmosphere, a non-metric unit. And 1 atmosphere equals 760 millimeters of mercury, which in turn equals 101.3 kilopascals. Now, how would we convert these atmospheres, these kilopascals, the millimeters of mercury? Well, we'll use those conversion factors. And as always, we'll write our given as a fraction over 1 inside parentheses, and we'll use cancellation to get rid of units that we don't need. And so sometimes we'll multiply, as in the top example, sometimes we'll divide, as in the middle example, and sometimes, as the example at the end, we'll have to do both. How do we convert these? Well, with the same way we converted pressure. Again, you'll write your given as a fraction over 1 inside parentheses, and we'll use cancellation to get rid of common units. So here we want to convert 2 calories into joules. The calories will cancel, and in this example, it's just multiplication. 8.368 joules, because the joules is the unit that didn't get canceled. Or we can have 600 joules over 1 multiplied by the same conversion factor, only flipped upside down. Here, the joules are canceled. We ignore the ones, and this is just division. 600 divided by 4.184 gives us 143.4 calories, because the calorie was the unit that wasn't canceled. Finally, we have a problem where you have to use back-to-back conversion factors, and so instead of 2 fractions, you have 3. We have 2 kilojoules, and we first convert that to joules, and then we convert those joules into calories. Canceling kilojoules and joules, so this becomes 2 times 1,000 on the top, that's 2,000. We divide it by 4.184 on the bottom, and we end up with about 478 calories, the unit that was not canceled. Now, temperature itself is done with devices called thermometers, which are often part of larger setups called calorimeters. A simple calorimeter might consist of a couple of styrofoam cups with a thermometer placed inside, and inside that some water. A more advanced calorimeter, like a bomb calorimeter, will have an electrical charge, and you'll actually blow up a sample of material, and you'll measure either the temperature change or perhaps the pressure change of some supply of oxygen. But in any case, thermometers are part of those setups used to measure temperature. Now, what thermometers actually are measuring is the amount of thermal energy in a system, which in turn is based upon the number of collisions at the molecular level. Those collisions between molecules or with the container holding the sample of molecules are said to represent the average amount of kinetic energy, which is pretty much the same as the thermal energy, the heat of the system. Different scales are used to measure temperature: Celsius, Fahrenheit, and Kelvin. Celsius has the freezing point of water at 0, Fahrenheit at 32 degrees, and Kelvin at 273. The Kelvin scale is a third scale, and like the Celsius scales, it's also part of the metric system, and it uses the same decimal scaling as the Celsius scale. You might wonder why we need it if it's the same. Well, it has to do with conditions outside everyday life, where we really want to accurately describe a system's thermal energy. One particular question of interest is the theoretical temperature at which molecular motion stops in the Celsius scale, which is sometimes called absolute zero. Again, on the Celsius scale, that's about negative 273.15 degrees Celsius. So to convert from Celsius to Kelvin, you simply add 273.15 to any Celsius value. Thus, 0 degrees Celsius is 273.15 Kelvin, and 100 degrees Celsius is 373.15 Kelvin. The Kelvin scale, again, is only preferred for temperature values outside everyday life. It can be used to accurately describe a system's thermal energy. Now, like many properties of matter, especially gases, the changes in temperature and pressure are best thought of as the result of the random motion of a complex system of many tiny particles absorbing or releasing energy. This is a very important point. Here you see this image in front of you, blue spheres and red spheres bouncing around inside a box. They represent about, say, 24 particles of some gas colliding with one another and with the sides of their container. How is this animation made? Well, someone wrote a computer program where they put in the masses and the momenta of what direction any particle was moving in any given moment, and then the computer calculates how they would bounce around one another, producing this animation. Well, this is possible because these aren't really a lot of particles. A couple dozen is nothing. If we were talking about the air inside my classroom, the actual number of particles in the atmosphere within my classroom is, hundreds of billions of times greater than the number you might see in this box. And thus, if you were trying to make an animation of it with a computer, lots of luck. I don't care what kind of computer you have, no matter how powerful, a realistic attempt to assess and predict the behavior of the vast number of particles, even just in a single high school classroom, is so great that probably no computer on Earth could actually do that calculation. Nevertheless, it's important to emphasize that this is the big idea in this set of notes. We have random motion of a complex system of many tiny particles absorbing and releasing energy. So complex, so tiny, there's no way to actually follow them all. This is the essential idea behind what is called kinetic molecular theory. It describes a gas, again, as a large number of particles, atoms or molecules, all of which are in constant rapid motion, that has randomness arising from their many collisions with each other and with the walls of the container. Kinetic molecular theory uses this idea to explain the properties of gases, including pressure, volume, and temperature. Kinetic molecular theory takes advantage of the fact that while individual atoms and molecules are nearly impossible to follow, the behavior of a large number of randomly moving particles can be predicted with statistics. Kinetic molecular theory was suggested by the work of Robert Brown, who in 1827 observed tiny grains of pollen under the microscope moving without apparent cause. Check out the kind of microscope that Brown used. There was no internal light source, no light bulb, no, none of that. Instead, you wanted light and wanted a strong image, you would do something like, burn a candle fairly close to the microscope and then use the rotating mirror to reflect the light of the candle flame through the observation tube. These crude microscopes obviously required a great deal of skill. 1827, Robert Brown, who we might now describe as something kind of like a biologist, Robert Brown was looking through a microscope in his living quarters, and he was trying to take very good care not to bump the table the microscope was on, not to jar it while he was looking through it, and yet when he made careful observations of these circumstances, the tiny grains of pollen under his microscope appeared to be kind of jiggling and kind of moving around randomly. Brown at first thought that that might be evidence that the pollens were actually capable of independent locomotion, like independent organisms. Later on, however, he accomplished the same observation of randomness, not with something that came from a living thing, because pollen does come from plants, but from debris left over in his fireplace, coal dust, little specks that looked like little grains of pepper under the microscope. And yet, while they did not come from a living thing, they appeared to be moving around under that circumstance. And so this strange phenomenon, unexplained for many decades, was called Brownian motion. In 1905, this fellow, Albert Einstein, proposed this phenomenon could be explained statistically as the result of a motion of a large number of tiny particles, and in the process provided evidence for the existence of atoms. This image shows a gold particle, and it's being bombarded by other things that look like little specks of sand, and it's undergoing what the mathematicians call a random walk. And the random walk of a particle in Brownian motion is simply the statistical result of countless random collisions with other particles much smaller than the one being tortured over and over again in this animation. Now, kinetic molecular theory requires a number of assumptions which might not always be true, and these assumptions are made to simplify the math. And this is an important point. Sometimes people get the idea that a theory is just a hunch or a guess. Not so. It's actually a very powerful and useful object. But other people think, well, the theory is so powerful that it must be true, that maybe this is the final word on that topic. And that really isn't true either. When we talk about a theory, we're not talking about an absolute truth. Neither are we talking about something weak like a hunch or a guess. We're talking about a powerful explanatory and predictive model that works very, very well. So in kinetic molecular theory, we have this simple model, and it makes some predictions. One of the predictions or claims, conditions necessary for it to be true, is that there should be no attractive forces between gas molecules. Well, here we have water molecules. And you might say, well, is water a gas? Well, it is here, and at any given moment, a certain percentage of water is in the state of a gas. Right now, in your room at home or my classroom right now, a certain small percentage is made of water molecules in the gaseous state. How do we know this? Because we exhale water vapor with every breath. Now, here we make an assumption that there are no attractive forces between the gas molecules, but as the illustration reminds us, earlier on in this course, we discussed intermolecular forces in section 6.4. And those intermolecular forces are mentioned again in our current section, 7.1, on page 206, 207. And so if you didn't read that material in the previous unit, when you come to page 206, 207, you may be puzzled by what we mean by intermolecular forces. If that's the case, I strongly recommend you reread section 6.4, because we went past that pretty quickly. Having said that, though, this is an example right here in the inset. These water molecules, notice that the hydrogen sign shown in blue labeled delta plus, they are pointing toward the negative side of another water molecule, the oxygen side labeled delta minus. And so this weak attraction is a hydrogen bond. It's an example of the kind of intermolecular forces, and it does happen to be a force of attraction. So kinetic molecular theory is actually, it makes this assumption, but the assumption isn't true. Well, if it isn't true, why do we make this assumption? Well, we do it because it makes the math easier, and because a lot of the times those attractive forces don't really matter very much. Now, another assumption made by kinetic molecular theory is that the molecules are in a constant state of linear motion. In this picture, which is on the first page of chapter 7.1, we see a bunch of molecules inside a box, and they hit each other and they're hitting the sides of the box. But after they collide, they move in straight lines. This assumption of straight line motion simplifies the math. But it is a simplification that ignores other forces that might promote nonlinear motion, circular or elliptical curving motion, things like gravity or electromagnetic fields. But most of the time, those objects' influence is not very great. And so this is a reasonable assumption to make, especially for relatively large samples of a gas. Another assumption is that the collisions between molecules are perfectly elastic, that is, that they lose no energy when they collide. Well, this really isn't necessarily true. Carbon dioxide is quite a bit larger in size than, say, an individual hydrogen. And so if they collided, both moving at the same speed, well, the collision would not be perfectly elastic. The hydrogen would be moving much faster after the collision, and the carbon dioxide perhaps a tad slower. But this, while not being a true assumption, is actually irrelevant when we're looking at a large sample of a gas. Why? Because overall, the amount of energy loss equals the amount of energy gained by some other part of the system. The net loss of energy by the system is usually so small that it's negligible. And so we can make this simplifying assumption that, while not really true, doesn't really affect the outcome for the kinds of calculations we do. Finally, we claim that kinetic energy is proportional to temperature. That is, the kinetic energy of the molecules in motion of the system are, the same thing as the temperature. Well, not quite, because it is possible that things can affect the average kinetic energy of the system, but their origin is not the actual particles themselves. For example, radiation from the sun, solar radiation, can heat up a system, and it's a source of energy that's not based upon particles colliding. Nevertheless, we can ignore that. Why? Because if you have a system that's receiving sun, most of the time they're all receiving about the same amount of radiation within the system. And so it is still roughly proportional, even if not all the energy is due to the collisions of the particles themselves. Now, one circumstance where we do have to really call out where the kinetic molecular theory really fails at its predictions is when we have conditions of extreme temperature, extremely high temperatures, or extremely low pressures. And the key one is absolute zero. This is a condition where the local temperature is getting so low that it means that kinetic energy of the system is approaching zero, and in theory, all motion could stop. In those circumstances, KMT doesn't really make accurate predictions. And that's a particular area that if it were be the subject of study, if you were doing, say, low energy physics, well, you would just know right away that you would not be using just KMT. You would be using other kinds of math to supplement it to get more accurate results. So, it seems like I'm apologizing a lot for KMT here, like it's a sad thing that it doesn't really work well, but it actually does work very well in most of the circumstances we encountered. In a high school course, almost every circumstance we encounter, kinetic molecular theory is adequate. And even at higher levels, kinetic molecular theory is used most of the time, because most of the time the assumptions we make, while not actually true, don't impact the math that much. If we were in a circumstance where it did impact the actual result, well, we would have to add more math to supplement or perhaps replace KMT. But even those limitations can prove useful. So for example, they were using KMT in some experiment. This theory provides a useful baseline for investigation. When the predictions of KMT don't match up well with the actual experiments, why, that's a clue that the chemist needs to dig deeper. And so we would go away from the normal KMT and go to some other kind of model where we have more advanced math to describe a more complex circumstance. Boyle's law is going to involve pressure. And again, pressure is simply the force applied by a gas over a given area. The formula is pressure equals force divided by area. It's measured by pascals and kilopascals in the metric system. And we might also have to convert from pascals to kilopascals we might have to use non-metric units like the atmosphere or millimeters of mercury. When we use the conversion factors where 1 atmosphere equals 101.3 kilopascal, which equals 760 millimeters of mercury, this reminds us of how these units were developed in the first place. The non-metric units like atmospheres and millimeters of mercury were derived from the original barometers. These barometers were fairly large setups. They measured the pressure of air on an open reservoir of mercury. Mercury is a toxic metal, but it's also a metal which is liquid at a room temperature. And so if the atmosphere presses down on a big, large open reservoir of mercury, an inverted glass tube with markings on it can receive that mercury. That is, the pressure on the entire pool of mercury will force a thin line of that mercury to rise within that glass tube. And the higher it rises, the greater the local pressure. And so this fact can be used to measure the local pressure in terms of millimeters of mercury, the actual height to which a column of mercury in one of these original barometers would reach. And so it is a metric unit of sorts, and it's certainly derived from a standard that we can appreciate and understand. Now, long before the development of kinetic molecular theory, careful experiments with similar devices similar to the barometer I just described, they allow scientists very early on in the 17th and 18th centuries, before Robert Brown, before Albert Einstein, it allowed those earlier scientists to detect patterns in the properties of gases. These patterns, expressed as simple equations, are often referred to as the gas laws, and they allow chemistry students today to easily predict how changes in the properties of gases affect one another. Now, you might see them here and you might think, oh my goodness, it's algebra, and it might look a little terrifying, but look at the letters we're using. I think if you think about it, capital P, well, that's just going to refer to the pressure. Capital V, that's just going to refer to the volume, and capital T is going to just refer to the temperature. So a lot of these gas laws is just pressure and volume, or pressure and temperature, or volume and pressure, and there's simple relationships. They're either multiplication relationships or they're division relationships. And so this is much simpler math in the statistics that has to be used if we're going to go beyond kinetic molecular theory. And so we're just going to rehearse some simple techniques, multiplication or division with fractions, canceling out some units, just the same sort of things that we've done before, but it will allow us to figure out a whole bunch of things. Our first such law is Boyle's law, and you'll see the expression says P1 V1 equals P2 V2. Well, what's 1, what's 2? Well, they're just different times. And so what this literally means is the pressure times the volume at one time, at the first time, is somehow going to equal the pressure times the volume at some later time, at a second time. This law was first proposed in the 17th century by Robert Boyle. You see him there. Boyle used gadgets that kind of look like leather shoe boxes, fairly large, and they had things that kind of look like pistons that you could push in or out of the leather box to either increase or decrease the volume at the same time that a simple pressure gauge was attached to the interior of the box. And so this law is based upon his observations using those gadgets. And he observed that if you change the volume that was available to a sample of gas inside one of his leather shoe boxes, it also caused the pressure within that leather shoebox contraption. It changes the pressure that gas is able to exert on the inside. Specifically, Boyle's law states that for a given sample of gas at constant temperature, the volume varies inversely with pressure. That is, if one goes up, then the other goes down. If P1 goes up, P2 is higher than P1, then you can bet that V1 will go down when it's V2. If the volume goes up, you can bet the pressure goes down, and vice versa. It's an inverse relationship. And so the product of the two variables, PV, is a constant. So pressure times volume before the first time will equal pressure times volume later the second time. Another thing, however, which is often not noticed, is that the graph of an inverse relationship like Boyle's law is always a curve. And we might wonder, why is this so? Well, it's because in principle, the pressure can approach zero. And if the pressure approaches zero, then the volume could be infinite, any size, or the volume could get smaller and smaller. It could approach zero, which means then the pressure could approach infinity. Why do we get a curve? Because one part of the curve is going to slant up and point toward infinity, and the other point will point towards zero, and vice versa. All right, students, you've heard the notes, got a technical explanation of the formula for Boyle's law and the kind of graph it produces, but now it's time to actually solve a problem. So I'm going to take my trusty Sharpie and we're going to go to the whiteboard. So let's use my data projector. We're going to figure out how to solve these problems right now because I'm going to show you how to do them in real time. Okay, so here we go. Our formula says that we're going to have P1 equals V1. I'm going to go ahead and just write that out. P1 equals V1. Or rather, P1 V1 equals P2 V2. Now, what does this actually mean? Well, it means that we're going to take the pressure multiplied by the volume at some time, the first time we measure it, and the pressure times the volume the first time we measure it is going to equal the pressure times the volume when we measure it some time later, the second time we measure it. That's all it means. It's a constant. So let's say we've got a balloon, right? And we're going to say that this balloon has a pressure of 4 atmospheres. We'll start by using the unit of the atmosphere. We're going to say that the volume of this balloon is 2 liters, and that's before. And then we're going to say that later that the volume of the balloon decreases. It becomes just 1 liter. And so the question is, what is the new pressure? P2 is unknown. So this would be like you take a balloon that's a certain size, and then you would like squeeze it from the side. And when you squeeze it from the side, you would actually make the volume bigger, or sorry, you'd make the volume smaller, right? If you squeeze it, you're reducing its volume. And the question is, what happens to the pressure? Okay, so we're going to take our variables and we're going to write them out by plugging them into the equation. When we do that, since we're doing multiplication, if we actually have a number in a unit, we're going to put the number in the unit inside parentheses. So we have P1. P1 is the first thing given, so we're going to write 4 atmospheres. And then right next to it, we have V1, and that's given. We have 2 liters, so we put that in its own separate parentheses. And then, P2 is an unknown, so we just write P2. And then V2 is known, so we put that in parentheses, just like that. What we want to do is we want to solve it so that we have just P2 over here. We want to solve for P2, right? Because P2 is the unknown, that's the whole point. So we want to get rid of that 1 liter, so we're going to divide this whole expression by 1 liter, which will cause that to cancel out. Of course, whatever we do to one side, we have to also do to the other. So we'll put 1 liter over here. Now, obviously, the 1 liters will completely cancel out on the right-hand side. But less obviously on the left-hand side, just the unit of the liter will cancel. And so this is going to become 4 atmospheres times 2 divided by 1. And I'm pretty sure you can do that in your head. 4 atmospheres times 2, yes, the answer is 8 atmospheres because that is the number and the units that were not canceled. Pretty straightforward. So now let's go ahead and keep the same basic setup, and we'll do a different problem. This time we'll solve for an unknown volume. Formula doesn't change. And you know what? I think we'll continue to use balloons, but we will change some units. This time we're going to say that we have a pressure in atmospheres, and we're going to say that our pressure in atmospheres is actually not in atmospheres. We'll say it's in millimeters of mercury, and I'll go 600 millimeters of mercury, and the volume of the balloon will be 3 liters. And then at some unknown time in the future, the pressure in the balloon will increase. It'll be 1,800 millimeters of mercury. And, well, the volume is unknown. The question is, what will the volume be? Okay, so that's what we do. We always write out our variables. All these problems will always have 3 variables given. You write them out, and then we're solving for the fourth variable, whatever it is, wherever it is. Okay, so P1 is 600 millimeters of mercury. And we multiply that times 3 liters. So that's our left-hand side. And then P2 is given, it's 1,800 millimeters of mercury times an unknown V2. Now again, we want to solve for V2, so we want to get rid of everything that's there. So to do that, we're going to divide this side by 1,800 millimeters of mercury. But of course, whatever we do on the one side, we have to do the other as well. So of course, these two things completely cancel out. And less obviously, the millimeters of mercury cancel out. We have something cute here. 600 times 3 on the top is 1,800 liters. And here on the bottom, we've got 1,800, right? So 1,800 divided by 1,800, that's right, the whole thing's just going to be equal to 1. 1 watt? The answer is 1 liter, because that's the unit that wasn't canceled. So we had an unknown pressure before, we had an unknown volume. Now what we're going to do is, instead of looking at things that come after, we're going to have a variable problem where we know what happened afterwards, but we don't know how it got started. I mean, it's the same math. It doesn't actually matter if you're solving for what came before or what comes afterwards. So this time we're going to solve for what came before. Okay. And I'm going to use a different unit for pressure. I'm going to use the Pascal. I'm going to say that afterwards, that when we get done, we're going to have a pressure that's equal to 200,000 pascals. And well, what's the size of this thing? We're going to say it's 400 milliliters. Instead of liters, it'll be milliliters. Now, we don't know what the pressure is when we got started. That's our unknown, but we're going to say that we know precisely that the volume of the balloon was 1,000 milliliters back in the day when we got started. Okay, so again, we always write out our 3 known variables with the number and the unit, and we put a question mark by the unknown, and now we plug it into our equation. We're solving for P1, so we just write P1, and then next to it, the number and the unit for V1 is given, so we put that in parentheses right next to it. And then we're going to go over here. P2 is 200,000 pascals. And V2 right next to it is 400 milliliters. Now our unknown is over here. It's P1. We want to solve for P1, so we want to eliminate anything that's next to it. So that's 1,000 milliliters. And we'll do that. And of course, whatever we do to one side, we have to do the other side. This, of course, completely cancels. Here, we just cancel the unit of the milliliters now. Now, this is a little tricky, so just remember, this is 200,000, that's 400. Well, 200,000 divided by 1,000 is just going to be 200. So really, this is just 200 times 400. So when we get done doing the math, what do we discover? We discover it's 80,000. 200 times 400, 80,000 watt. The answer is pascals, because that's the unit and the substance that wasn't canceled. All right, so that's an example of how to do the Boyle's law problems. They're all multiplication. They're all set up like this, and we use cancellation of terms to figure out the value of our unknown. And I hope that was helpful.